Hello everyone, I'm Liang, comes from the Global Energy Interconnection Research Institute company. Today I'd like to make a presentation to show our work, an anomaly detection method based on GCN and the correlation of high-dimensional sensor data in power grid system. The presentation includes 5 parts. They are introduction, related work, methodology, experiments, and conclusion. The first part, introduction. In recent years, an increasing number of sensors has been developed in the physical world. IoT data and their analysis are becoming a hot topic because they can provide a consistent way to access sensor data. One of the most important purposes of analysis of sensor data is to detect potential anomalies in them. Anomaly detection is the process of discovering anomaly data in data resources based on various data processing models and techniques. Traditional anomaly detection mostly targets outliers based on statistics, distance, density, and clustering. However, these methods usually consider sensor data in isolation and ignore correlations between sensors. In the real world, there is a certain connection among the data of sensors. One sensor data may be normal on its own, but may be anomalous when considered together with other sensor data. So, a correlation-based sensor data anomaly detection method is proposed to address the above issues, and the main contributions of our work are listed on the screen. Firstly, we try to capture the correlation of multiple monitoring data and represent it as graph data, which will benefit anomaly detection in the power grid system. Secondly, we use GCN to learn the correlation graph data, which will detect the changes in the correlation data. The principle behind this method is the assumption that multiple monitoring data will impact others in a certain time. The third one, experiments on power quality data size, demonstrates that the proposed method outperforms several anomaly detection methods. Then, related work. Anomaly detection methods for outlier points can be broadly classified into 4 categories, which are statistical-based, distance-based, density-based, and clustering-based. In addition, there are 3 main cases of anomalies in temporal data. The first one is contextual anomalies, which are point anomalies in temporal data. The second type is a subsequence anomaly, whose subsequence pattern is very different from the pattern of the overall sequence. The third type is an anomalous sequence that is different from the base sequence. Recently, some research on anomaly detection of time series data has been done. However, there are various challenges in anomaly detection of time series data, such as the length of the subsequence is difficult to determine efficiently. The anomaly does not appear in training set, and there is often relatively large noise in the time series and so on. As a result, we propose a correlation-based anomaly detection method for sensor data that can dynamically discover the relationships between data at runtime and find data anomalies based on them. Next, the methodology. Our method tried to capture the correlation of time series data and its latent relationship. This correlation between time series data could be represented as graph data. Moreover, we trained GCN to classify the new high-dimensional data. The details of the methodology is shown on the right side of the screen. In the left part is the training process. We calculate the correlation coefficient and feature of this sensor data to build graph data, and then the GCN-based model is trained as classification model, which is applied to detect possible anomaly in unlabeled sensor data. Then I will introduce the 3 steps of the methodology. The first step, the calculation of correlation coefficient. Firstly, the sensor is often in the form of time series data, and we can use a fixed time window to calculate the correlation coefficient for each pair of them. Secondly, we calculate the correlation between the features according to different correlation calculation methods to obtain different time series correlation matrices, and then merge the correlation matrices into a 3-dimensional matrix array, as shown on the right side here. The second step of the methodology, the feature selection. As the number of sensors increases, the number of correlation coefficients will also increase. Many anomaly detection algorithms are difficult to solve high-dimensional data anomaly detection well. So, in this paper, we designed a correlation selection function, which is used to select correlation coefficients according to the relationship between the two data relevant strength and stability. The formula used here is shown on the screen. Then is the third step of the methodology, the GCN anomaly detection model. We take advantage of GCN in extracting correlation features between nodes and apply it to the power indicator correlation graph for anomaly detection. Our goal is to establish a correlation relationship between various power indicators within a period of time, so as to detect anomaly event when it occurs or will occur in the power network. As shown in the figure on the right side of the screen, firstly, a correlation coefficient-based graph data are prepared based on different data sources. Then, some certain anomaly and non-anomaly graph data are labeled to construct a supervised dataset. Finally, we train the GCN to find the relationship between the power indicators which can classify and detect anomaly events in this time series data. Next, I will introduce the experiments part. Firstly, I would like to show the datasets we used in this paper. The datasets used in our experiments are the real sensor data and artificial maintenance records from power quality data of charging posts in the region. Dozens of power quality data measurement points for the number of charging posts have been deployed in the region. The detailed information of the datasets is shown in the table. As you can see, there are 3 datasets. Then I will introduce the details of the experiments and the results. Our experiment is conducted in a desktop computer with configuration as follows: CentOS 7.7, 4-inch i7 8750 CPU, 8 GB RAM, and 200 GB hard disk. Then the result and analysis. We compared our method with 2 commonly used anomaly detection methods, which are SVM and CNN. We applied SVM to learn a model to determine whether the new data belongs to a specific class. If it does not belong to this class, then it is anomaly. CNN. The baseline method uses CNN to detect anomalies in time series data. The CNN has 4 layers in our paper. Then GCN correlation. This is our method. We capture the correlation of time series data and their latent relationships. We train GCN and classify the new high-dimensional data based on these correlations between time series data. The results are shown on the screen in the table. As you can see in Table 2, SVM, CNN, GCN correlation, this is our method. We can see that GCN correlation consistently outperforms the other methods in different datasets. Compared with SVM and CNN, our approach pays attention to the correlation of each time series data. By modeling the varying relationship of each time series data, we can better mine the relationship between the anomaly and the change trend of each time series data, and then use the graph convolutional neural network to detect the time series anomaly. Finally, the conclusion. We propose a data-driven anomaly detection method for handling sensor data. The proposed method builds graph data based on correlation analysis, and then use graph convolution to capture changes of sensor data, which can analyze changes of dynamic sensor data in the IoT environment. Our method performs anomaly detection of multi-dimensional sensors and obtain higher accuracy. We apply our method to the anomaly detection of the power quality data in power grid systems, and we verify that our proposed anomaly detection method can detect anomalies with high precision and recall through a series of experiments. That is all of my presentation. Thank you for your listening.